All right, today's lecture will be from section 7.7, all about positive rational exponents. We have been dealing with exponents, and they mostly have been positive numbers, but now we're going to give it a little more detail of what can and cannot be our exponent. So take a look here. We want to evaluate any exponent when our base is greater than 0 and n is a rational number. Now remember, we've described n here as a rational number, which means it's anything that can be written as a fraction. So really our exponent could look like a fraction. We want to be able to simplify expressions or solve equations using these rational exponents. Solve the equations of the form x to the n equals b, where n again can be a rational number. And then recognize the different properties that we've already previously shared when it comes to positive rational powers, like bases, add the exponents, power of a power, multiply them. Those are just a couple. So let's get started. So remember, what is rational? Anything that can be written as a fraction. Any type of number that you can put in the form a over b. It could be top-heavy, like 3 over 2. It could be proper, like 2/7. But with fractional exponents, there's two parts to your power now. And we would like to say that the numerator represents the power and the denominator represents the root. So make sure x to the m looks like a normal power, but 1 over n would be the idea of a root. So I've written here, you could do the root first, x to the power of 1 over n, that to the power of m, or you could do the power first and then the root. Now here we're talking about non-negative numbers as our base. So we want to think of positive numbers dealing with these x. So let's go ahead and try a couple. Let's do these first. Now, noticing that each one of them has a whole number as the base and a fraction, that fraction being either top-heavy, improper, or proper. We don't want to use a calculator because we're saying you should be able to do these. Now my first question is, what should I do first? And that's a discussion we didn't have on the previous slide, but you want to think about it. If you have no calculator, do you want to take these numbers and look at some of the base numbers and raise them to the powers first with no calculator? Or would you like to deal with the root of that number, which means you'd actually be making your original number smaller? I hope that statement has solved the dilemma. You definitely want to, with no calculator, root first. So think of it, if the top number is the power, if the top number is the power and the bottom number is the root, you want to do the root first. Okay, because you will be making your number smaller. Then you will have a smaller number that you will have to power. So the denominator represents the root. So if I rewrote this 8 to the 5/3 and put the root first, I'd be thinking of it as 8 to the 1/3, that whole thing to the 5th, which means if I multiply those exponents, power of a power, I would get 8 to the 5/3, which is what it was originally. So here we go. What is 8 to the 1/3 power, or what is the cube root of 8? Most of you do that in your head quite nicely, and you get 2. That leaves now 2 to the 5th is all you need to do. It's easier to take 2 to the 5th power than it would have been to take 8 to the 5th power. So 2 times 2 times 2 times 2 times 2 for a total of 32. Our final answer on that one is 32. Now, you don't have to rewrite them every time like this, but at least that's how you have to think. So 27 on the next one has to be cube rooted. What's that one number that multiplies by itself 3 times to give you 27? And that answer is 3. Go ahead and square it, because that's all that's left for the power, and you get 9. So you're doing the root first, which is the denominator, then you're doing the power. 32 to the 3/5. So now we're doing 32 fifth root. What is that one number that multiplies by itself 5 times to get you to 32? Now remember, it can't be that big. Okay? So knowing that, we had done it up here, right above it. It's related, so our fifth root of 32 is 2. Now we got to go to the third power from there. 2 times 2 times 2 would give us our 8. So they are sort of backwards of each other. They undo each other. Think of it that way. Over here, 36, square root, because that's a 2, we know is 6. You now have to the third. Now some of you start panicking because you can't multiply 6s that big. Hey, 6 times 6 you already got is 36. Scratch a piece of paper, you got 36, and you got to multiply that by 6. 6 times 6, 36, carry the 3. 6 times 3 is 18, and 3 is 21. So we end up with an answer of, we'll go this way, 216. That's probably one of the bigger ones you'll have to do. If you have to use scrap paper, that's fine. But when it does say, do with a calculator, or do without using a calculator, please force yourself, because you're not going to get any better. Challenge yourself. Okay. Probably we're looking at the end of the chapter having something without a calculator as well. Maybe there'll be 1 or 2 on the test. Hard to say at this point, but keep that in mind as we move forward. All right, from here, question is, how big am I? If I don't give you any numbers, you're looking at x to the power of m over n. You've seen all kinds of sizes here. Most of them have been whole numbers. Now I want you to think. If x is greater than 1, so x is a positive number bigger than 1, and m over n is greater than 1. So what we're saying there, it is an improper fraction. How big will our answer be expected to be? And you can look at some of these. Where x is bigger than 1, I'd go back to the 8, that looks good, and m divided by n is greater than 1. So 8 turned into 32. We're not looking at what size is it really in relationship. We're saying, what is it? Well, it has to be bigger than your base. It has to be, bigger than x. Okay? And x was greater than 1, so it has to be, x has to be greater than 1. When x is greater than 1 to begin with also, but your m over n, rational exponent, is a number between 0 and 1. In other words, it's proper. What's going to happen? And the answer is, looking at it, I will be looking at all these that were of that situation. I see 27 to the 2/3, 32 to the 3/5. You started with a base of 27. Your resulting answer was 9. You got a base of 32. Your resulting answer is 8. So what's going to happen? It's going to be smaller than x was originally. Notice, none of them have become negative numbers. So if you want to say, x is greater than 1, it's just going to be smaller than x was itself. Okay, anything else on that page? No. All right, moving on. Simplify. Now we're getting fairly big. Let's put these down one at a time. That is not going to be one that you're expected to do in your head. So you really have two ways you could do this. You could pick up your calculator and do them individually like we were doing. Or you could, our calculator doesn't have fractional exponents in, so we will put the number in by itself. Let me clear mine off. You should do the same with yours. So we need 42,861. So we put the base number in, and now because that is our exponent, you want to remember that you have your base number in. You're going to use your caret key to raise it to a power, but because I am a fraction, all fractions must be in parentheses. So raise it to the power of 5 divided by 6 on your calculator, and do not forget to add those parentheses. And you're now looking at an answer. As we said, a lot of them on the previous page were all whole numbers because they were perfect combinations. On this one, we're looking at a 7,245.225654-ish. They would probably be rounding directions, and right now we're going to say it's approximately 7,245.23-ish. Simplify. So you can still take roots of numbers, just like you did a square root. A square root of 24 was not a nice whole number. It was a decimal, messy, kept going, irrational number. You're going to get that same look in some of these. So what happens if we have solving the equation? If we're solving the equation, that means we need to get y by itself, which has always been our goal. But to get y by itself, some people like to say, well, don't I have to do this separately, meaning rewrite this? And the answer really is no, because in your brain you have to say, well, I am a fourth power and a cube root. So how do I undo a fourth power and a cubed root? Most people's answer will be take a cube of the cube root and take a fourth root of a fourth power, which really means if we used the reciprocal exponent of what's there on both sides of the equation, notice what's going to happen. Our left side, which is exactly what we want, cancels totally and we just get a 1. So that's the same as y. We want y by itself. And on this side, we're now looking at a rational equivalent. So brain says, what is that one number that multiplies by itself 4 times to give me 625? And most people say, oh, well, that's 5. And then 5 cubed would be back to our answer, which is 125. So now if you wanted to do a check, you could take 125 to the power of, in parentheses again, 4 divided by 3, close the parenthesis, and you would get that 625. So you can do these, but you've got to remember to use the reciprocal power. That would be to be able to do this in one step versus 2. Undoing the power would be one step. Undoing the root would be the second step. All right, let's see what else we've got. If we go to real life story problems, then look carefully. This one says a formula which gives the approximate volume V of a soap bubble in terms of its surface area, A, is V equals 0.094 A to the power of 3 halves. So you are seeing that rational exponent used right here in approximating the volume of soap bubbles. Now, when are you going to do that? Who knows? Who knows what you're going to be doing? But if it says find the volume of a soap bubble with a surface area of 20 centimeters squared. So start taking a look at your formula, and you can see from our work here, V equals 0.094 is part of the formula, times A, which stood for our surface area. So we would put in our 20 centimeters squared for A, and know that we're going to take it to the 3 halves power. Now remember, we have a volume that we're looking for. Our label, we already know volume is cubic units, so our label really doesn't have to be there to sort of, as we say, mess up our calculation. So I'm just going to take our label out of there so it doesn't get you in trouble. And now here we go. I look at that real quick, see if it's something I can do in my head. I'm thinking 20 to the 3 halves, that's a square root of 20. That's not a nice number. So pick up your calculator. You already have that decimal in there anyway, which means you're going to have to later on, if not right at the beginning, go to the decimal form. So 0.094 times, in parentheses, 20. Close the parenthesis, raise it to a power of 3 halves. If you don't like 3 halves, putting it in parentheses, remember, you could go 1.5, and you wouldn't need parentheses there. And now we're getting a volume of 8.6 8.40761-ish, so 8.41-ish approximately is our answer. And going back to the label, we had centimeters squared, so our volume would be centimeters cubed. So that's what we're looking at, how we can analyze. We're going to see more and more problems that have fractional exponents. That's what this one was about. Not that you're going to have to come up with the formula, but you are definitely going to have to be able to manipulate with exponents of the form 3/2 rational fractions. All right, with that, you have enough information to move forward. They will be all positive exponents today, and we'll move on to the negative ones in our next section. So bring any questions you have with you to class. That's all for now.